Monocular depth estimation is widely used in robotics and computer vision. We recently made a video on Apple's ML Depth Pro method. This was newly released by Apple and it works on doing accurate monocular depth estimation. Now, in order to understand the applications and to see how we can implement monocular depth estimation methods, these networks, on practical use cases such as autonomous driving, I wanted to showcase how to do that and how we can measure the performance. So stay tuned until the end of this video. Welcome back to the channel, guys. My name is Dhruv. I am an engineer at Convolve AI. I hold a professional engineering designation in Ontario, and at Convolve AI we assist small, medium, large enterprises with their problems that can be solved using computer vision and AI. If you are looking for any assistance, here is our contact information. Feel free to contact us and we would be happy to help. In this video, I am going to showcase the application of Apple's ML Depth Pro method on Virtual KITTI 2 dataset. Virtual KITTI 2 dataset, for those of you who don't know, is a clone, or you can say a replica of the actual KITTI dataset. So KITTI dataset is an autonomous driving dataset that has been widely used in a lot of autonomous driving research. Virtual KITTI is a virtual form of that. It's essentially a virtual clone of the original KITTI dataset. And this dataset comes with a lot of different information. It has RGB, it has depth maps, and it has a whole lot of other things, including semantic segmentation information. We're going to use this Virtual KITTI dataset and we are going to run the Apple's ML Depth Pro on the Virtual KITTI dataset RGB images. We're going to see the depth output and we're going to compare with the ground truth depth maps that come with the dataset. So stay tuned until the end to see how all this magic happens. The purpose is threefold here. Firstly, to showcase how you can practically use these models, these machine learning models, on an actual dataset, on an actual setup. So by showing how to use this model on Virtual KITTI, we accomplish that. Secondly, to understand the Virtual KITTI dataset and to understand the implementation behind using that dataset, and also using the ML Depth Pro model to obtain the depth maps or depth map predictions on the Virtual KITTI dataset. And thirdly, just for fun, to see the effectiveness of the method. So we will understand and go into the details about how well this model performs when compared to the ground truth depth maps. So guys, here on the screen, you can see the Virtual KITTI 2 dataset. So this is what the dataset looks like. On the screen, you can see this particular GIF or animation showcasing this data with different weather conditions. So these are RGB frames in different weather conditions. And it also has the semantic segmentation information, plus it has the depth information. So if we go into the details of this dataset, here are all the files that come with the dataset. You can see there is RGB, there is depth, there is class segmentation, instance segmentation, even optical flow is there. So for the purpose of this particular demo, all we need is the top two folders or top two files. These are the RGB images as well as the depth images from the data. If we just go a little bit into the detail of these two modalities in terms of the data, for RGB, it's as expected 8-bit 8-bit image with 3 channels, so that's pretty standard. And for the depth, it is a 16-bit grayscale image, so a single channel image with 16 bits, so it's a UINT16. And for a fixed far plane, they use 655.35 meters as the furthest distance, which means in the depth maps that come from the ground truth, 655.35 meters is the farthest value, is the largest value, and you won't see any information more than that in the depth map. And this also is because of the 16-bit encoding limitations, right? All right, guys, so that's how it is. Now let's go into the details and let me show you the dataset. So here, guys, is the Virtual KITTI dataset. So inside of the Virtual KITTI, I have downloaded the RGB and the depth information. So let me first showcase the RGB. If I go here, there are different scenes: scene 1, scene 2, scene 6. These are different scenes in the dataset. So different sequences that are being recorded in different areas. If we look at scene 1, there are 15-degree left, 15-degree right, 30-degree left, 30-degree right. These are different cameras. And then there are these different different weather conditions: clone, fog, morning. So let me show you an example of 15-degree left first. Um, So here you can see this is a camera which is essentially facing a little to the left with rotated by 15 degrees. And let me now show you the clone, which is essentially a clone of the original Kitty sequence in a virtualized world. And then we have fog, morning, overcast, rain. So that particular virtual world now has been added with different weather conditions to be able to test your algorithms, to be able to train your algorithms, etc., etc. So let's see the clone here. This basically clones the original data set. This is what it looks like, right? So guys, you can see as compared to the 15-degree left, this is looking straight. This is one of the cameras. So the Kitty data set has a stereo pair, two cameras, camera 0 and camera 1, and we are going to work with camera 0. This is the sequence, guys, we are going to use. And these are some of the sample images that we are going to run Apple's model on. So for those of you who did not see the last video, here is on the screen, you can see the last video's information. You should watch that video on how to set it up. But this essentially is the Apple's ML Depth Pro, and we have the code as well. So using this code, we had set up this model, and then we had created scripts on top in order to run the inference on Virtual KITTI dataset. This is the paper. If you're interested in going into the details, you can read this paper. Now guys, let's look at the code. So here is the code. The first thing is we've modified the code for Depth Pro to run inference on the Virtual KITTI dataset. So in order to understand this, this function over here is just a function to save the depth map. And the way this function is working, it takes the predicted depth. It is going to clip the depth between 0 and 655.35. 655.35, mind you, is that particular farthest depth value in the original ground truth images from the Virtual KITTI 2 dataset. So any prediction from the network from the depth map, we also clamp it at that value, because we don't want to compare the predictions which may have up to infinite depth values to the ground truth, which is truncated, which is clamped. So here we do that clipping using NumPy clip function, and then we encode and we change the video, the depth map into uint16 data type. Using that, we save that particular depth map as a PNG file. All right, next over here, this line number 26, we are essentially just loading the model, which is the Depth Pro model. We are loading it onto our GPU, and then we are setting it for evaluation. We are setting up the evaluation mode. Next is the data path. This is the directory, the path to the directory where the ground truth data is, or the RGB data is, and that's the path to this directory that I've shown you already. So this exact path is the data path, and then we essentially get the list of all the images that we are going to run our inference on, and then this is the path where the results are being saved. Now guys, this is a very simple for loop which is essentially iterating over all the images in that data directory. We load that image and we transform it as per the Depth Pro requirements, and next is we basically run the inference to get our depth values. Once we have the depth values, we essentially call the save depth png function and save the depth maps to our output folder. So let me show you some of the output depth maps. So these are the output depth maps. These are the predictions from the Apple's ML Depth Pro model. Now guys, this is a uint16 file that we are visualizing. The visualization is not as clear. The depth map is not normalized. So what you see may look not very pleasing to you, but we are saving it in this way just because the Kitty dataset, Virtual Kitty datasets depth maps are also similar to this. Now, guys, if you were to normalize this, it would look a lot different, and it would look a lot better where you could see the cars very clearly. Let me just quickly show you the actual Kitty ground truth depth maps here. So for that, we just go into the depth folder, phone, frames, camera 0, and this is what the original RGB, sorry, the ground truth depth looks like, and this is the ground truth, and this is predicted. So guys, just looking at this, you see that, you know, for the ground truth, it's very sharp along the edges of these leaves and all. The Apple output is not as sharp. Of course, this is in a virtualized environment, so the ground truth depth would of course be very crisp as compared to a model output. Just to give an example, guys, this is what a normalized depth map would look like. So on the screen, you can see this one. Mind you, this does not come from the Apple's ML Depth Pro. This is from another model, which is Depth Anything, which is one of the baseline models ML Depth Pro compares against. But if the depth map is normalized, this is what it would look like. It wouldn't look very dark as you saw the previous one over here. Right. So now that kept aside, let's compare all the depth maps between the ground truth and the predicted depth map from the Apple's algorithm. So here on the screen, you can see the video showcasing the depth maps, right? On the top is the ground truth, and at the bottom is the prediction from Apple's algorithm. So as far as I can tell, it's pretty nice. The predictions are good. The depth maps are very similar. Of course, the ground truth is much sharper in certain areas, but nevertheless, the Apple's output is not too bad, right? It is noisy. You can see in the sky, it is predicting a lesser depth value than the actual, but still, it's not as bad as one would expect, because again, guys, this model has never, this is a completely pre-trained model, pre-trained weights downloaded from the internet. It has never seen Virtual Kitty data. We've never trained it on Virtual Kitty. It's a model that we're directly running on the Virtual Kitty dataset. Okay, so guys, now that we have the model has run, we know how to set this code up, we have understood how to run this code. Again, if you are interested in understanding the setup of this system, we do have another video that we created on how to set up Apple ML Depth Pro, and also the GitHub repository has the instructions on how to create the virtual environments and install all the libraries related to it. Now, after we are done getting our outputs for the inference on the Virtual Kitty sequence, we essentially get this a folder directory with all the output images. Right now, our job is to compare the output depth images with the ground truth and see how well the Apple algorithm has performed. So guys, this code over here essentially has functions to calculate different metrics. So the metrics we are going to use here are RMSE, absolute relative error, mean absolute error, and delta less than 1.25 for our comparison purposes. Now guys, if you don't know how these metrics are calculated, we won't go into the details in this video, but you can leave your comment in the video, under the video, and if you'd like, I can go over the details of how or how we define these different metrics: the RMSE, the mean absolute error, the absolute relative error, and the delta 1.25 error metric for depth supervision or for depth comparison. So mean absolute error over here, this is the code. It's essentially comparing it's the root mean square error between the predicted depth and the ground truth depth. Second is the absolute relative error. So in short, it's basically taking the difference between your predicted depth map and the ground truth depth map and dividing it by the ground truth to get the first part is the absolute error, and then to get the relative error you divide it by the ground truth and you get the relative error, and of course you take the mean of the entire image to get the mean absolute relative error. Delta less than 1.25 error, this one is a little tricky. It basically goes by a ratio, so you're taking ratio between your predicted depth map and the ground truth depth map, and vice versa. You're taking whatever gives you a bigger value, and the goal is that you want maximum or majority of your depth pixels to have a ratio of 1.25 or less. That means that when you compare your predicted depth map and the ground truth and take the ratio of the two, majority of the output of from that ratio should be 1.25 or less, which means the prediction and the ground truth is very close to each other, right? So higher the delta, the better it is, the better depth prediction your algorithm has done. All right guys, and then last is mean absolute error. This is very simple. You just take the absolute difference between your prediction and your ground truth and you take a mean of that. This function here is to plot a histogram of your predictions and your ground truth, just to understand the profile, just to understand what it looks like, and we will take a deeper look into this. Alright guys, now comes the evaluate depth map function. So this is the function where you iterate over all the different frames, all the different depth images that you have predicted and the ground truth, and you compare them against each other and calculate the error metric. So here we are essentially initializing empty lists for each of the metric. Here we have the ground truth file, which we get from the ground truth directory. So which is the directory I already showed you over here. Over here are all the ground truth files, and over here is all the predicted files. You get a list of ground truth as well as the predicted files, and this loop here is where you are iterating over each of the ground truth and the predicted file, and you are the next step is to essentially obtain first the path to the each of the ground truth and the predicted file in that list. Then you load the ground truth and the predicted file onto a numpy array using cv2.imread. You give it the path to your ground truth, and this argument here is saying that do not change, do not truncate the image, because our depth image is a 16-bit image. If you do not pass this im read unchanged argument, cv2 will truncate it to uint6 uint8 array or uint8 image instead of uint16, which will lead to a significant loss in information from your depth values. So this is very important when you are working with depth maps, especially for Virtual KITTI 2 dataset. And then we convert it into float. This essentially converts the uint16 to a float 32 array, and we divide it by 100. And the reason we divide it by 100 is just because when the uint16 is saved, everything is in centimeters, so we bring it back to meters for the ground truth and the predicted depth. Now guys, here we calculate the RMSE, we calculate the absolute relative error, delta error, as well as the mean absolute error. and all of this is being appended into those output lists. Once once your function has done iterating over each image and calculating metric for each single image, all you do is call obtain the mean inside of each of the lists. So you will have RMSE scores for each image predicted and ground truth pair. Say in this particular data set there are around 477 images for that particular sequence, so you'll have 477 values in each of these lists. You take the mean of that, and that is your average RMSE and average absolute relative, average delta, and average mean absolute error, and then you return that. Here to call, we essentially have the directory, just the ground truth directory, and then we have the predicted directory, and we call this function. So let's run this and see what we get as the output. So here 477 images, this is running in real time. It's going to give us the output, right? So here is the output. I've already put it in a table over here. So guys, here we can see the output from our Apple ML Depth Pro evaluation code. So we see that the root mean square error is around 47.7 meters. Absolute relative error is 0.241. The delta error is 0.6, which is around 60%, which means 60% of the prediction and 60% of the ground truth have a ratio of 1.25 or less, right? So the higher this number is, the better is the metric. And then mean absolute error is 11.4 meters. Now guys, again, this is Apple's model, which was never trained on any of the KITTI dataset. It was trained purely with other datasets, and we just took it and ran inference on the KITTI dataset. And these are the numbers that it reported. Not too bad. Again, if you go to Virtual KITTI 2 datasets benchmarks, you'll see much better performance. But of course, in this video, I did not expect, or through this experiment, I did not expect perfect performance. Even though like the performance it is given with regards to the scale of the depth, as well as the values are pretty accurate. It's not too bad. Having said that, since this was never trained on the Virtual KITTI dataset, I think the performance is reasonable. So that's it for this video, guys. We have gone over how to use the Apple ML Depth Pro, or for this purpose, you could use any other depth model out there, and how you can run it on another dataset. For example, in this case, we took the Virtual KITTI 2 dataset, and we showed you how you can run the inference for the model frame by frame on the dataset. After you run it frame by frame, you put it in different directories. You can then run evaluation to evaluate how well your model has performed. So we have gone over the evaluation code, as well as gone over different metrics that we used for the evaluation purpose. Again, if you need more clarity on the metrics, please leave a comment below, and we would try to do a video on that. That's it, guys. Thanks a lot for watching. If you like this video, please hit the like button, subscribe to the channel, and hit the bell icon so you are notified about any new video that we upload. Thanks again for watching, and I'll see you in the next video.